Let's start with a couple of simple but powerful questions. Why doesn't the solvent peak completely ruin every proton NMR spectrum? And why did one compound, TMS, become the universal ruler for chemical shifts? The answers lie with two quiet but essential components of NMR spectroscopy: deuterated solvents and deuterated standards. In this video, we'll explore what they are, why they are absolutely critical for NMR experiments, and how to choose the right solvent or standard for your specific application. These are concepts that every NMR user encounters, but not everyone truly understands. Imagine trying to hear a whisper in a room full of people shouting. That's exactly what happens when we try to run proton NMR using normal solvents. Common solvents, like methanol or chloroform, are packed with hydrogen atoms. Proton NMR detects hydrogen nuclei, so the solvent produces extremely strong signals. If we used regular solvents, their peaks would dominate the entire spectrum, completely drowning out the signals from our compound of interest. This was the first major challenge in the early days of NMR. How do we dissolve the sample without overwhelming the signal we actually care about? When we look at this visually, the problem becomes even clearer. A regular solvent contains many hydrogen atoms, and each one contributes to the NMR signal. The result is an overcrowded spectrum where the solvent peaks are far stronger than the sample peaks. Instead of clean, interpretable data, we get a spectrum where important information is buried or lost entirely. So the failure of normal solvents isn't about chemistry, it's about signal dominance. And solving this problem required thinking beyond ordinary hydrogen. The solution came from a clever isotope swap. Hydrogen was replaced with deuterium, an isotope that contains one proton and one neutron. Chemically, deuterium behaves almost the same as hydrogen, so it dissolves compounds just as effectively. But spectroscopically, it behaves very differently. Deuterium resonates at a completely different frequency than hydrogen, which means it is essentially invisible in proton NMR. That's why solvents like CDCl3, D2O and DMSO-D6 became standard tools in NMR laboratories worldwide. Deuterated solvents play another critical role that often goes unnoticed. They provide the lock signal for the NMR instrument. Magnetic fields are never perfectly stable. Over time, small fluctuations occur. The deuterium signal acts like a GPS system for the magnet, continuously correcting these small drifts. Without this lock signal, peaks would slowly move, broaden, or become distorted. So deuterated solvents don't just make spectra readable, they help keep them stable and reliable. Chemical shifts in NMR are not absolute values, they're relative measurements. That means every spectrum needs a reference point. This is where deuterated standards come in. Compounds like TMS, DSS, or TSP define the 0 point of the chemical shift scale. TMS became the gold standard because it is chemically inert, produces a single sharp peak, and is easy to remove due to its volatility. However, in aqueous systems, water-soluble standards like DSS are preferred. Choosing the right standard ensures consistency and comparability across experiments. Choosing a deuterated solvent is not a one-size-fits-all decision. It's more like choosing the right tool for the job. First, consider polarity. Is your compound non-polar or highly polar? Second, think about proton exchange. Does your molecule contain OH or NH groups? And finally, check chemical compatibility. Will the solvent react with your compound? For non-polar organic compounds, CdCl3 works well. For polar or ionic compounds, DMSO-D6 or D2O is often the better choice. And for hydrogen bonding studies, solvent choice can dramatically change what you observe. Even experienced NMR users run into practical issues with deuterated solvents. One common issue is water contamination. Even high-quality deuterated solvents contain trace amounts of H2O, which show up as small peaks in the spectrum. Another issue involves exchangeable protons. OH and NH signals may disappear completely in D2O due to proton-deuterium exchange. Finally, some solvents can be chemically reactive. For example, CdCl3 can form acidic impurities over time, which may degrade sensitive samples. Using fresh solvents and proper storage helps avoid these problems. Deuterated solvents remain essential well beyond basic proton NMR. In carbon-13 NMR, stable solvents support effective proton decoupling. In two-dimensional NMR experiments, solvent suppression becomes critical for achieving good resolution. And in quantitative NMR, solvent purity and isotopic consistency directly affect integration accuracy. At advanced levels, solvent choice becomes part of the experimental design itself, not just a routine step. To wrap things up, deuterated solvents and standards are far more than laboratory accessories. They stabilize the magnetic field, define chemical shift references, and clarify spectral signals. When chosen wisely, they transform noisy data into clear, meaningful insight. The right deuterated solvent and standard can turn a good NMR experiment into a great one, shaping the story your spectrum ultimately tells. Thank you for watching, and feel free to reach out if you have questions.